So hi guys, so today we will solve this like TIFR 2025 part B, like true and false type questions, like from question 1 to 5. Uh, yeah, the first question says that uh, if G is a group of, so order of G is given to be 361, then G has a normal subgroup H such that H is isomorphic to G by H, right? So we know 361 is 19 plus 19 square. So since 19 is prime, so basically, so we know group of order p square is abelian. Okay, so where p is prime, of course, where p is prime, where p is prime. So basically, this will be abelian. Now, basically, by the fundamental theorem of on abelian groups, like basically, like G will either be isomorphic to basically Z19 square, or it can be like isomorphic to like basically Z19 cross Z19. Okay. So in our former case, say, I mean, in our latter case, say, uh, G is isomorphic to Z19, so cross Z19, right? So basically, it is saying that G has a normal subgroup H such that H is iso. So I mean, yeah, because I mean, this will have subgroups like natural. I mean, very naturally, this will have subgroups like this, right? And uh, sorry, this will be cross Z19, right? So these are subgroups of this, and we can see if we take a projection map. Let's say, okay. So let's say we take a projection map. Uh, Basically, this goes to zero, right? I mean, so if we take a projection map, the kernel will be basically, yeah. So let's just say, so this will go to a comma 0 bar, right? So the kernel of this car pi will be basically 0 bar cross Z19, right? And using the first isomorphism theorem, yeah, we can say this. Okay, now if G is isomorphic to Z19 square, right? Since okay, so basically like yeah, so order of G is, yeah, 19 square, right? So basically it will be a uh, so basically there will, like, of course, using like uh, Cauchy's theorem or by using silo, whatever the case, we can say that there will exist a subgroup H of G whose order is 19, right? And similarly, we can, since of course it's abelian, this will be normal, and we can uh, quotient quotient it by this. So G by H, like quotient of G by H will also have order 19, so it will be isomorphic to, let's say, Z19. So yeah, we can like see that this will be the case. So first, okay, so first option is true. Okay, now number like now second question. Okay, in the second question, it says that there exists a metric space X such that the number of open subsets of X is exactly to 2024. Since, oh, sorry, by the way, this is not 2025, this is 2024. Yeah, that's why like they gave a question. So there exists a matrix space X such that the number of open sets of X is. So is this true or false? So basically, number of open sets are finite, right? First observation is number of open sets of X, which is a metric space is 2024, which is nothing but finite. Now then X has to be finite, right? Then X has to be finite. And this will be the case because say uh, like say X is not finite, right? Say X is infinite. Say X is infinite. Now basically since x is t2, basically it's t1, so basically it's matrix space, right? So basically singleton x is closed, right? Singleton x is closed. So basically singleton x is closed. So it means its complement. So basically x complement, which is nothing but x minus this. This is open. Okay. Now, okay. So if x is infinite, like we can get many, like infinitely, we can take infinitely many points, and for each x, x minus that will be open. So basically, number of so this will imply. So basically, this will imply that uh, number of open number of open sets of number of open sets of x is infinite, right? Since x is infinite, so yeah, so we have proven that this is an open set. Sorry, this is a finite set. So x is a finite set. Now, if x is finite, right? So now, and it is also a metric. We can all. I mean, it's given that x is a metric space. So x will be discrete, right? Because like we can just suppose finite. So say the number of elements of, let's say, x is n. Now then, so basically dxi xj. So this set basically says that, right? Yeah. So says that xi comma xj belongs to x, where I comma j. So this set is well ordered, right? So there will be a minimum, and we can just divide the minimum by 2, and we'll see that each point is isolated and so on. So, and we can see that this will be a discrete metric. Now, in a discrete metric, uh, I mean, each set is an open set. So basically, like therefore, x is discrete, and so total number of open sets is total number of open set of x is 2 to the power cardinality of x. So in this case, 2 to the power n. So basically, our like this set will be of the form 2 to the power n. Okay, but 2 to the power n for some n is 2024. I don't think so, because we know that 2 to the power 10, I think, is 1024. So 2 to the power 11, I think, will be 8402048, right? So yeah, so that is not possible. So this one is false. Okay, so question number 2 is false. For question number 3, it says that the function, so we have given a yeah, so the function d r cross r to r given by this defines a metric on R. So it is already given this is a metric, but nonetheless, if it was not given, then it will, I mean, then it's very easy to show that this is a metric, because this is an injective function, right? This is continuous increasing, yeah. So I mean, strictly increasing, so it's injective function, as we can see, e to the power curve of e to the power x. So yeah, this will define a metric, obviously. And so, acha, and with respect to the metric, R comma D is a complete metric space. So basically, we are given a metric, and it is saying that R comma D is a complete metric space, like with respect to the given metric, right? Okay, so let me try to solve this. So let me try to solve this. So, so basically, we are given R and D, where D is D of D of x comma y. D of x comma y is e to the power x minus e to the power y. Okay. Now what we can do is, let's say, try to define a bijective isometry to another set, right? Okay, to another matrix space. So let me define fx. Okay, so sorry, let me define f r with this d metric to 0 comma infinity with the usual metric, right? With the usual Euclidean metric by saying like x goes to e to the power x, right? X goes to e to the power x. Now, f is surjective, as we can see that f is surjective, and yeah, since fx is increasing, so f is surjective and injective as well. So injective as well, right? Because it's strictly monotone, so and continuous. So it's yeah. So f is injective as well. So now yeah. So now uh, so d of x comma y, which is given by e to the power x minus e to the power y, which is nothing but d usual, which is nothing but uh, yeah, which is nothing but okay, which is okay. So this is nothing but f of x minus f of y, and my mod of my f of x minus f of y, which is nothing but uh, the usual of fx comma fy. So basically, the map will preserve distances. So basically, this is an isometry. So basically, uh, f is a bijective isometry. F is a bijective isometry, which implies which sorry, let me give a comma here, which implies uh, RD, right? This is complete if and only if 0 infinity with respect to our usual metric is complete. Okay. So and it is easy to see because if like yeah, this is easy to see because if we have a Cauchy sequence which converges here, right? So yeah, we will. I mean that sequence. Yeah, since it will converge to a particular and since f is I mean okay since yeah, if this is complete, then it will converge. Now f is continuous, right? So and we can see that since f is why f is continuous because it's an isometry. So and by also using this map, so we can say that this is complete uh, biconditionally. This will also be complete. Okay, so yeah, because like this is complete. Any Cauchy sequence will converge here. Now f is continuous, so yeah, so if it's continuous by sequential criteria, then f will be Cauchy continuous by, I mean, yeah, by sequential criteria, this will converge there. And okay, so I mean, we don't even need that. We can just use the fact that this is a isometry to show that this will converge to some that, yeah. So, okay, so but we can clearly see that this is not complete because 0 infinity is not complete because we can take a sequence 1 by n, right? This converges to 0 as n tends to infinity, and yeah, 0 doesn't belong to the set, so not complete. So since 0 infinity is not complete, which implies r comma d is not complete. Okay, so our this option is false. Yeah, this is also false. Now for so basically we have done 1, 2, 3 pretty easily. Now what about 4? Basically we are given a positive integer n, and it is said that m is a sorry, A is a n cross n. Basically, A belongs to M and R, such that okay, A cube is identity. Okay, A cube is identity. Then A is diagonalizable in M and R, and and they have given the definition of the. I mean, what do you mean by a diagonalizable matrix? So yeah, so basically then A is diagonalizable in M and R. Okay, so is this true or false? So this is question number 4. I guess. This is question number 4. So this is question number 4. Right. So basically, A belongs to M and R, and A cube is identity. It satisfies this. So basically, so basically, uh, okay. So basically, yeah, so basically this is annihilating polynomial. So annihilating polynomial is x cube minus I. Now we know that minimal polynomial of this will divide x cube minus I, which is nothing but x minus sorry, this is x cube minus 1, right? Not I, because it's in like that Rx. So Rx. So yeah. Uh, so this 1 plus x squared, right? So so if minimal polynomial of this is x minus 1, then A is I diagonalizable. So basically A will be an identity matrix and diagonalizable. So for any n, so this will be diagonalizable. But say minimal polynomial of this is 1 plus x square. Then, and let's say we take say say we take n equals 2. Okay, sorry, I don't know why I did it. So let's say we take n equals 2, then yeah, so let's take n equals 2, then basically, yeah, since n equals 2, then minimal polynomial, so basically characteristic polynomial, so we are taking a particular n, will also be 1 plus x square. And basically we can like, so but since this is not like the minimal polynomial, uh, so this is not like in R, like distinct linear factors, we cannot factor it, and basically it's irreducible, right, in R, irreducible in R. So which will imply that A is which will imply that A into R is not diagonalizable, right? Yeah, and we can take example of such matrix. So we can take the companion matrix 0. We can take the companion matrix 0. I think 1 minus 1. Yeah, minus 1. Yeah, something like that. So this will not be diagonalizable, and so we are done. So basically we are done with. So this will also be false. So question number 4. So question number 4, we have completed question number 4. So question number 4 is also false. Now, question number 5, it says that if A belongs to, okay, so M and Q, the field is Q, okay, such that the characteristic polynomial of A is irreducible over Q, okay, and then A is diagonalizable in M and C. That's a both similar type of question about this. Uh, okay, then A is diagonalizable in M and C. Okay, so let us try to solve this one question. Okay, we have enough space here, so let us try to solve this. So they are saying that this belongs to M and Q. Now, uh, okay, I forgot the question. Okay, just give me a moment. Uh, okay, the characteristic polynomial is reducible over Q. So the characteristic polynomial is reducible over Q. So characteristic polynomial of this is irreducible over Q. Now we know. So now they are asking that if is A like diagonalizable over right. So over C, right? MNC, I mean over C, over the field C. Now since this is irreducible over Q, right? Now if okay, so now we know that we know mean this will divide this characteristic polynomial, right? Okay, but from this we get uh, minimal polynomial of this characteristic polynomial of C. basically we have the same minimal and characteristic polynomial. Now one thing is, if we can show like if that in C, like this splits, like I mean basically, I mean if a minimal polynomial x splits into, you know, distinct linear factors in C, then basically A is diagonalizable. So let's see if that happens or not. Otherwise it's not, right? So let's see if that happens or not. Now this will happen because, right, we know that Q is separable, right? Q is separable, and since which means that uh, which means that since this is irreducible, so this will split into distinct, I mean characteristic of Q is 0, right? So it is separable, and because any field with characteristic 0 is separable, and such uh, will split into distinct linear factors in, okay, sorry, in its splitting field. Okay, so but see my, I mean, yeah, in its splitting field. Okay, so it will split into distinct linear factors in C. So which implies that this A is diagonalizable, which implies that A is diagonalizable. So yeah, so basically this will be true. So this we have completed, this will be true. The first will be true, rest three will be false because once again for this will be a discrete, I mean 2 to the power some power, and for this, as I have shown you, like the bijective isometry, if this is complete, this then that will be complete. It's wise one. I mean, it's an if and only if statement. Uh, Now basically, right. Um, Now for the fourth, I have already shown that 1 plus x squared is not diagonalizable, and for the fifth, it's true because Q is separable. So this is like the solutions from 1 to 5.